A stadium. That doesn't sit on land, not on concrete, not on steel foundations. It floats. Right in the middle of one of the busiest skylines on Earth, tens of thousands of people gather. On what is essentially a giant platform, drifting on open water. No solid ground beneath them. Just a structure engineered to behave like there is. And that's where it gets strange, because this isn't a temporary stage or a floating gimmick. It's designed to hold massive events, heavy equipment, and entire crowds, all balanced on something that was never meant to support it. Which means every second it exists, it's fighting physics. And if even one part of that balance fails, this isn't just a structural problem, it becomes a disaster. Singapore doesn't think like most cities. It can't, because it doesn't have the luxury of space. Every square metre is planned, negotiated, optimised. Skyscrapers compete for air, roads compete for land, and every new project has to justify why it deserves to exist at all. So when the idea of building a massive event venue came up, there was a problem. There was nowhere to put it, not without tearing something else down, not without sacrificing land that was already doing something valuable, and in a city where land is one of the most expensive resources on Earth. That wasn't an option. So instead of building on the city, they looked at what the city wasn't using: water. At first, it sounded impractical, even reckless. Water moves. Water shifts. Water doesn't hold still. And it definitely doesn't hold thousands of people, heavy lighting rigs, massive stages, and the kind of infrastructure a modern stadium demands. But that's exactly what made the idea so compelling. Because if it worked, it wouldn't just solve a space problem. It would redefine how cities think about space entirely. And Singapore had already been pushing those boundaries. This is a country that has expanded its own land by reclaiming it from the sea. That builds upward, outward, and sometimes in ways that feel almost unnatural. So the question wasn't, is this possible? It became, how far can we push it? The answer was bold. Instead of fighting the limitations of land, engineers decided to remove land from the equation completely. They would build a stadium that floats. Not a temporary floating stage tied to a dock, not a small platform for niche events. A full-scale, multi-purpose venue designed to host national celebrations, major performances, and thousands of spectators, all sitting above open water with nothing solid beneath them. And it wouldn't just sit there passively, it would have to stay perfectly stable, perfectly balanced, perfectly secure. Because unlike a building on land, this structure would be constantly interacting with something unpredictable. Every ripple, every current, every shift beneath the surface. Which meant this wasn't just an architectural challenge, it was a physics problem. And solving it would require building something the world had never seen before. At first glance, the concept sounds simple. If ships can float, why not a stadium? But that comparison falls apart almost immediately. Ships are designed to move. They're built to glide with the water, adjust to waves, and constantly shift their balance. A stadium can't do that. It has to feel motionless. Because the moment people feel even the slightest instability, the illusion breaks. And in a structure holding thousands of people, that's not just uncomfortable, it's dangerous. So the challenge wasn't just making it float, it was making it feel like it wasn't floating at all. The answer came from a principle that's been understood for centuries, but never pushed to this scale: displacement. If you push enough water out of the way, the water pushes back. That's what keeps massive ships, oil rigs, and floating platforms from sinking. But those structures are designed for function, not precision. This needed both. Engineers designed a giant steel platform, roughly the size of a football field, supported by a series of massive hollow pontoons beneath it. Think of them as giant airtight chambers, carefully calculated to trap just enough air to keep the entire structure above water. But here's where it gets more complicated. It's not just about staying afloat, it's about staying level. Because when thousands of people move, when equipment shifts, when wind pushes across the bay, the weight distribution changes constantly. And if the platform tilts, even slightly, that shift multiplies. So the entire structure had to be balanced with extreme precision. Weight had to be distributed evenly. Load limits had to be controlled. Every movement had to be accounted for before it even happened. And then there's the part most people don't think about. Anchoring. Because a floating stadium that drifts isn't a stadium, it's a problem. So beneath the surface, hidden from view, a system of anchors and stabilizing connections locks the platform into position, allowing it to rise and fall gently with the water, but never drift away from it. From above, it looks effortless, but underneath, it's a constant battle between gravity, buoyancy, and control. And that balance is what makes the entire structure possible. Standing on it, you wouldn't know. No swaying, no drifting sensation, no reminder that beneath your feet, there's nothing but water. And that's not accidental. Because the biggest threat to a floating stadium isn't sinking, it's movement. Even the smallest shift, something you wouldn't notice on a boat, becomes amplified when thousands of people are standing still, expecting solid ground. Human balance is incredibly sensitive. A slight tilt, a subtle vibration, and suddenly the entire structure feels unstable. So the real challenge wasn't keeping the platform above water, it was eliminating the feeling of water entirely. To do that, engineers had to control something that's constantly in motion. The bay itself. Beneath the surface, the platform is connected to a network of anchoring points, not rigidly fixed, but carefully tensioned. These anchors don't fight the water directly. Instead, they absorb and distribute its energy, preventing sudden shifts while still allowing controlled, minimal movement. Think of it like a shock absorber system, but on a massive scale. At the same time, the structure's weight is spread across multiple floating sections, each designed to counterbalance the others. When force is applied in one area, whether it's wind, waves, or the movement of people, that force doesn't stay isolated. It's redistributed, smoothed out, neutralized before it can be felt. And then there's another layer most people never consider: timing. The platform doesn't just react to movement, it's designed to anticipate it. Engineers studied how crowds behave, how weight shifts during events, even how synchronized movements, like cheering or jumping, could affect stability. Because if thousands of people move at once, the structure has to handle that surge instantly. All of this works together to create something unusual: a floating structure that tricks your brain into believing it's completely still. But that illusion comes at a cost, because the more stable it feels, the more precisely everything underneath has to perform. And if that precision slips, even slightly, the effects don't stay hidden for long. Designing it was one thing. Building it was something else entirely. Because unlike a normal stadium, you can't just pour concrete, set foundations and build upward. There's no stable ground to work from, no fixed base to rely on. Everything has to be assembled on something that moves. And water doesn't wait for you to get it right. Every wave, every tide shift, every change in weather introduces uncertainty. Even small movements can throw off alignment, delay installation, or force engineers to recalibrate entire sections. So instead of building it piece by piece in the water, they built it somewhere else first. The entire floating platform was constructed in sections, massive steel modules assembled with precision in controlled environments. Each piece had to be exact, because once it reached the water, adjustments would become far more difficult. Then came the delicate part: transport. These enormous sections weren't just lifted into place. They were floated out into Marina Bay, carefully guided across open water like oversized puzzle pieces. Tugboats maneuvered them into position inch by inch, with almost no room for error. Because once they were in place, everything had to connect perfectly. No gaps, no misalignment, no second chances. And even when the structure was assembled, the job wasn't done. It had to be stabilized in real condition. Wind loads had to be tested. Water movement had to be monitored. Structural stress had to be measured under shifting weight. Because what looks calm on the surface isn't always calm underneath. Then there was another challenge, one that had nothing to do with physics: time. Singapore wasn't building this just as an experiment. It had a deadline. The platform needed to be ready for major national events, which meant delays weren't just costly, they were unacceptable. So construction didn't just have to be precise, it had to be fast. And that combination, speed, scale, and instability, is where most projects fail. But somehow, this one didn't. piece by piece, connection by connection, the floating platform came together. Not on land, not on a fixed foundation, but on water that never stops moving. And when it was finally complete, what emerged didn't just look unusual, it looked impossible. From the outside, it looks flawless. A stadium floating effortlessly against one of the most iconic skylines in the world. Clean lines, smooth water, a perfect illusion of control. But what you're seeing is only the surface, because making something like this work doesn't come without trade-offs. The first is capacity. Unlike traditional stadiums built on solid ground, this platform has limits, strict ones. Every extra tin matters. Every piece of equipment, every lighting rig, every structure added on top has to be carefully calculated. You can't just scale it up, because the more weight you add, the more you push against the very force keeping it afloat. So while it can host large events, it can't behave like a conventional mega stadium. There are invisible ceilings, limits the public never notices, but engineers constantly work around. Then there's maintenance. Water isn't passive, it corrodes, it seeps, it slowly wears down anything that sits on it long enough. Which means the structure beneath the surface is in a constant battle against rust, against pressure, against time. Inspections aren't occasional, they're continuous, because small problems underwater don't stay small for long. And then there's something even more subtle: flexibility. On land, structures are rigid, fixed, predictable. This isn't. No matter how stable it feels, the platform is always responding to currents, to wind, to weight shifts. It's controlled, yes, but never completely still. And that means every event, every setup, every movement has to be planned differently. Nothing is truly standard. But the biggest trade-off isn't structural, it's psychological. Because the entire experience depends on one thing: the audience believing they're standing on solid ground. The moment that illusion cracks, everything changes. And that's why so much of this project is designed not just to function, but to remain invisible. Because the more you notice what's happening underneath, the less stable it starts to feel. At first, it looks like a one-off, a bold experiment, a visually striking project designed to stand out. But that's not what this really is. This is a preview, because the real problem Singapore was solving isn't unique to Singapore. Cities everywhere are running out of space. Land is limited, demand isn't. And as populations grow, as events get bigger, as infrastructure becomes more complex, the traditional way of building on fixed ground within fixed boundaries starts to break down. So the question changes. It's no longer where can we build? It becomes, do we even need land at all? That's what this project quietly answers. Because once you prove that a structure this large, this heavy, this complex, can exist on water and function like it's on land, you unlock something much bigger than a stadium. You unlock flexibility. Imagine event spaces that move, infrastructure that adapts, entire districts that expand outward instead of upward. Floating architecture stops being a novelty and starts becoming an option. And in places where land is scarce, expensive, or already overbuilt, that option becomes incredibly valuable. But it also introduces a new kind of responsibility, because building on water isn't just about engineering anymore. It's about control. You're no longer working with something static. You're building on a surface that's constantly changing, constantly responding, constantly demanding precision. Which means the systems underneath have to be smarter, stronger, more controlled than anything we've relied on before. And that's the real shift. This stadium isn't just a structure, it's a statement that cities are no longer limited by the ground beneath them, but by how far they're willing to push beyond it. Because once you step off land, there's no natural boundary left, only engineered ones. And those boundaries can always be pushed further. So the next time you see it, a stadium floating perfectly still on open water, it might look like stability, but underneath, it's constant motion, constant calculation, constant control. And the real question isn't how long it can stay afloat, it's how long we can keep everything beneath it perfectly balanced.